So the next topic that we're going to talk about is ocean acidification. I know it's kind of weird talking about the ocean. We've already talked about water, and we're talking about the atmosphere now. But ocean acidification is an atmosphere problem. It's an effect from an atmosphere problem. And what's happening is our ocean is acidifying. It's getting more acidic. Now this first part of this lecture is going to talk about the chemistry of ocean acidification. You may never have taken chemistry, so I'll kind of break it down to the basics and kind of give you some tips on things to remember and how to remember it. So our last lecture, we talked about climate change, and climate change is due to an increase in greenhouse gases, such as carbon dioxide and methane. Carbon dioxide, though, taking up the majority of our emissions. We've already seen this graph. We've seen how carbon dioxide is steadily increasing over the past century. But this carbon dioxide doesn't go just into the atmosphere. If we think back to our carbon cycle, remember there were 5 different places we could find carbon dioxide. In the atmosphere, which is where we're putting it, fossil fuels, soil, and organisms. But we also have the ocean. And remember that fast carbon pathway. That carbon pathway that has carbon dioxide that's in the atmosphere goes into the ocean, and vice versa. If carbon dioxide increases in the atmosphere, which is what we're seeing by burning fossil fuels, that means it's also going to diffuse and increase in our oceans. That down arrow representing carbon dioxide going into those oceans. So carbon dioxide is going to increase here in the ocean. And that's where this ocean acidification comes in. So although, yes, we're talking about water, the problem stems from the atmosphere and the increase in carbon dioxide in the atmosphere. This graph is showing similar to the previous graph. The red line representing the average atmospheric carbon dioxide. And here we can see it's growing. We saw that before. In blue is seawater or ocean water carbon dioxide. As you can see, it's more variable. It goes up and down quite a bit. But what you notice is that although there's a lot of variation, it's still increasing. And we expect that. As carbon dioxide in the atmosphere goes up, we would expect that carbon dioxide in water goes up. So this supports our claim that the ocean and atmosphere are in equilibrium with carbon dioxide. So what? So what if there's more carbon dioxide in the atmosphere? Well, the problem is that carbon dioxide and water make an acid. They make carbonic acid. So you know CO2 is our carbon dioxide, we've got H2O, which is our water, and we put them together. So this H2, so here's this H2, C, and then O3, O3. So even if you can't remember H2CO3 is carbon dioxide, all you need to remember is carbon dioxide plus water, and then add all those letters up together. And they make an acid. In this case, they make carbonic acid. Now this is a pretty weak acid. It's not like battery acid or something. But this is where the problem is. There is carbonic acid in our atmosphere. Think about clouds, things where water is, but the ocean is all water. So lots of carbonic acid being made. I'm going to take a quick aside to talk about the pH scale. The pH scale is what determines how acidic or how basic something is. This scale runs from 0 to 14. So you could say something has a pH of 14 or a pH of 10 or a pH of 3, etc. At 7, 7 is neutral. 7 is your drinking water, for example. It's not an acid and it's not a base. It's somewhere right in the middle. If you have a pH less than 7, this is considered an acid. If it's close to 7, that means it's not very acidic, and if it's close to 0, it's very, very acidic. So for example, like urine, that's acidic. Carbonic acid is somewhere around here. It's near coffee and tomato juice. And these are things we consume. I mean, we consume orange juice and lemon juice. So don't think carbonic acid, oh, it's going to dissolve your skin or something. It's about as acidic as coffee. And then if you have a pH greater than 7, these are what we call bases. Bases include our seawater. So our ocean water, and this is a number you should know, our ocean water has a pH of around 8. So the ocean is a little bit basic. But the problem is we are adding an acid. When you add an acid, you are going to lower the pH. So for example, if I take a pH of 14 and a pH of 0, if I mix equal parts of both of them, that's going to give me a pH of 7, somewhere in between. So with seawater, with a pH of 8, we are adding a pH of about 4.5. Now, we are not adding that much carbonic acid. It's not 1 part seawater, 1 part carbonic acid. But it is enough carbonic acid to lower that pH from below 8. And that's exactly what we're seeing. So the same graph we saw before, here is the atmosphere, carbon dioxide. Here is the seawater, carbon dioxide. And this blue line is following pH. And you see that the pH has been lowering in the ocean. It was around, when we started measuring, around 8.13, and now it's down to about 8.08, 8.07. So it's getting more acidic. 8.13 is more basic, and 8.08 is more acidic. However, these are both bases. These are both, above 7. It's still a base. We are not saying that the ocean is an acid. We're just saying it's becoming more acidic. This is like telling a 5-year-old you're getting older. We're not saying the 5-year-old is old, but they are getting older. Same thing here. The ocean is getting more acidic. Now you may think, well, that's not a lot. 0.13 to 0.07, that's really not a big difference. And you're right, it's not a big difference. But let me put it in perspective for you. In our blood has a specific pH. If our blood pH changes by 0.2 units, that could actually cause you to die. So small changes in pH have a really big effect, not just on the ecosystem, but our own bodies. So although the ocean hasn't changed that much, currently it's only changed about 0.06 or so, that doesn't mean it's not important. And that doesn't mean it can't wreak havoc on the ecosystem.